Hello and welcome back. In today's class, we'll be doing method of preparation of phenols. As you can see, I've written it here. So we'll be doing method of preparation of phenols and we'll be doing physical properties of alcohols and phenols. Well, as far the preparation of phenols is concerned, we can start with the first method we can start with is from sodium salt of benzene sulfonic acid, from sodium salt of benzene sulfonic acid, that is sodium benzene sulfonate. Well, I'll not start with sodium benzene sulfonate. I'll start from benzene because the question is framed like that in your textbook. Suppose I have a benzene molecule and I react this benzene with concentrated H2SO4. I can write it like this. On heating, it will break up into two parts, that is OH negative and SO3H positive. So SO3H positive is an electrophile in this case, which is going to attack on the benzene ring, leading to the release of H positive ion. That H positive ion will combine with OH negative and will come out as H2O. So I will get benzene sulfonic acid. This is the compound I am getting, benzene sulfonic acid. This, when reacted with NaOH, will give sodium salt. Because this is benzene sulfonic acid, so like other acids, it has a tendency of donating H positive ion. The H positive ion from this acid will combine with OH negative ion and will come out as H2O. And I will get sodium salt of benzene sulfonic acid. That's a compound like this. That is SO3Na, sodium benzene sulfonate. This compound on further reaction with NaOH, it will give me sodium phenoxide. I'll show you how the reaction occurs in this step. I will get this compound. Actually, one of the Na and Na from here will come out as Na2SO3, sodium sulfide. 2 hydrogen and 1 oxygen, they will come out as H2O. We are left with 1 sodium and 1 oxygen that will come on the benzene ring. This is sodium phenoxide. Sodium phenoxide on reaction with HCl will lose NaCl and you'll end up with phenol. So you'll get phenol. There is a question in your textbook, exercise question, in which it is given that you have been given benzene, sulfuric acid and sodium hydroxide. How you will prepare phenol from it? So this is the answer to that question. Next preparation we'll see. Second is from diazonium salts. So how to prepare phenol from diazonium salt? We'll see that. I'm taking benzene diazonium chloride in this case. So the compound I have got is N double bond N, Cl negative and positive, benzene diazonium chloride. If I heat it with water and if the temperature is more than 298 Kelvin, H from water will combine with Cl and they will come out as HCl. N2, 2 nitrogen, they'll come out as N2, nitrogen gas. So OH from water will combine with benzene, leading to the formation of a phenol molecule. So you'll get a compound like this, that is phenol. So this is how you can prepare from benzene diazonium chloride. Simply you heat benzene diazonium chloride with water and the temperature has to be more than 298 Kelvin. You'll end up with phenol. Next we'll see from Grignard's reagent. Third is from Grignard's reagent. Well, when I'm saying from Grignard's reagent, that Grignard reagent will be aromatic. So I've got a compound like phenyl, magnesium, bromide. Suppose this is the compound I've got. If I oxidize this compound by any oxidizing agent, I will get a phenoxy derivative of this. That is, I will get a compound OMgBr. This compound is phenoxy magnesium bromide. Well, most of the reactions of Grignard's reagent, they are always followed by hydrolysis. So in this case also, we'll carry out hydrolysis with a dilute acid. So H2O in the presence of H positive. H2O will break into two parts. This H2O is going to break into two parts, that is H positive and OH negative. H positive will substitute Mg positive. So you'll end up with phenol. You'll get a compound like this. This is phenol you are getting. The OH will combine with magnesium and bromine. That will form magnesium hydroxy bromide. So this is another method of preparation of phenol. So you can prepare phenol from sodium salt of benzene sulfonic acid, from diazonium salt, from Grignard's reagent. Now we'll see industrial preparation, large scale production of phenol. Industrial preparation. Well, if we talk about industrial preparation, we'll have two methods in that. The first one is from chlorobenzene, which we have already done in halogen derivatives. This method is known as Dow's process or Dow's method. In this method, we react chlorobenzene here I've got. I will react it with 2 moles of NaOH at a temperature of 623 Kelvin and 300 atmospheric pressure. At such a high temperature and pressure, one of the sodium will combine with chlorine. It will come out as sodium chloride. 2 hydrogen, they will combine with oxygen, they will come out as H2O. I am left behind with 1 of sodium and oxygen atom, which will replace chlorine. So I will get sodium phenoxide. I will get a compound like this, ONA. This is sodium phenoxide. This sodium phenoxide, when reacted with HCl, will lose NaCl and I will get phenol. This is what I am getting, phenol. The next industrial preparation that is given as a question in your textbook, exercise question. So next one is from cumin. We'll see how we can prepare phenol from cumin. Well, for that I need a molecule of propene. If I reacted with benzene in the presence of H3PO3, which is used as a catalyst, you will see Friedel-Crafts alkylation in this case. This alkyl group is going to attack on the benzene ring. I will get a compound like this. That is, here I will have CH, CH3, CH3. This compound is cumin. We'll see how we are getting this compound. Well, in propane, pi electrons, they'll move toward one of the carbon. This will become negative and this will require a positive charge. And the movement of electron will be like this only, because you know that 2 degree carbocation is more stable than 1 degree. So you'll get a 2 degree carbocation. This 2 degree carbocation will act as an electrophile. So it will attack on the benzene ring because benzene ring is electron rich. Any position where this carbon will attack, it will extract H positive ion from that position. That H positive ion is going to combine with CH2. It will form CH3. So here in this case, if you are seeing one of the CH3, this was actually CH2, which have CH2 negative, which have accepted one proton and has got converted to CH3. If we oxidize this cumin, we generally carry out aerial oxidation in this case. We'll get a compound like this, that is COOH, CH3, CH3. This compound is known as cumin hydroxy peroxide. So this is cumin hydroxy peroxide. This compound, when treated with concentrated H2SO4, breaks down into two parts. This part will come out as acetone. So you'll get a molecule of phenol. And along with that, you will get a molecule of acetone. This is how this reaction will proceed. And as I told you, this is given as a question, exercise question in your textbook. So this is all about method of preparation of phenol. By now we have done the method of preparation of alcohols and phenols. Now we'll move on to their properties. Whenever we talk about properties, we first talk about their physical properties, if there are any of any concern, and after that we move on to the chemical properties. Well, in this case, the physical properties, they are a bit important, and we'll see those physical properties. So we'll see their physical properties. Physical properties. As I told you earlier, physical properties basically includes solubility, melting point, boiling point, dipole moment, things like that. So here in this case, first we'll see their solubility. Well, unlike hydrocarbons and unlike alkyl halides, which we did, alcohols are more soluble in water. They are quite soluble in water. Now the question comes to our mind, how come they are soluble in water? Because alcohols, they have a tendency of forming hydrogen bonding with water. Suppose I have got a molecule of water like this. In these two bonds, I have a dipole where there is a positive charge on the hydrogen atom and a negative charge on oxygen. Now let us have a look at a molecule of alcohol also. It is also somewhat like this, oxygen negative and hydrogen positive. Then again a water molecule, oxygen negative and hydrogen positive. So you will see hydrogen bonding here. So alcohols are readily soluble in water because they can form hydrogen bonding with water. However, their solubility decreases as the number of carbon atoms in the hydrocarbon chain increases. Because as the number of carbon atoms in the hydrocarbon chain will increase, their hydrogen bonds will become longer and weaker. So alcohols having smaller alkyl groups are found to be more soluble, like methanol, ethanol, propanol, as compared to alcohols having larger alkyl group, like butanol, pentanol, hexanol, heptanol. So as the number of carbon atom increases, their solubility decreases. In this case, if we talk about the solubility of phenols, suppose I am talking about the solubility of phenol, I can say that phenol is like this. If I say whether it can form hydrogen bond with water or not, that is not possible because it has got a very large hydrophobic part. So this, in alcohol and phenol, we can say that they have two different type of parts, that is hydrophobic and hydrophilic. The alkyl group which is present there is a hydrophobic part, and OH group which can form hydrogen bonding is a hydrophilic part. So in phenols, the hydrophobic part is very large. That's why they have little tendency of forming hydrogen bond, and that's why they are less, or we can say they are sparingly soluble, where to a very less extent and on increasing temperature, maybe their solubility, it increases to some extent, but not very soluble. We can consider them as insoluble in water. So here we are considering them as insoluble in water. After solubility, we'll talk about their boiling point. Boiling point. Well, the boiling point of any compound in organic chemistry basically deals on the intermolecular forces. Now, suppose here I have got a molecule. This is a molecule I have got. This again a molecule I have got. This again a molecule I have got. They have some intermolecular forces among them. And we have to overcome these intermolecular forces. Then only they can move to their gaseous state. Then only they can be vaporized or they have their boiling point. Depending on that. Higher this force of attraction, higher will be the boiling point. Because then it will become difficult to overcome this force of attraction and make them to move in their vapor state. Now what about alcohols? No doubt, if we talk about these intermolecular forces, there are large different number of intermolecular forces. Like van der Waals forces, they are quite prominent. Means van der Waals forces, they are the integral part of these intermolecular forces. They are everywhere, van der Waals forces. But here in this case, when we talk about alcohols, along with these van der Waals forces, we have hydrogen bonds also. That's why they have slightly higher boiling points. So we can, if we compare alcohols with their corresponding hydrocarbons, suppose I am comparing an alcohol like CH3, CH2, OH. If I compare it with its corresponding hydrocarbon in that case I will write CH3, CH2, CH3. Corresponding hydrocarbon does not mean that I am comparing ethanol with ethane. Corresponding means nearly same molar mass. So ethanol has got nearly same molar mass as propane. If you got propanol, you will compare it with butane. So ethanols or alcohols, they generally have higher boiling point due to the presence of prominent intermolecular hydrogen bonding. If we talk about these hydrocarbons, suppose I am talking about this propane molecule. I have got another propane molecule here. The only intermolecular force they will have is van der Waals force. Whereas if we talk about alcohols, in alcohols, no doubt van der Waals force is there, but along with that, they have intermolecular hydrogen bonding also. And that's why they have higher boiling point. So alcohols have a higher boiling point. This is your exercise question in which it is asked why propanol has got a higher boiling point as compared to corresponding hydrocarbon. And that corresponding hydrocarbon is butane. It is because butane has got only van der Waals forces, but propanol along with the van der Waals forces has got hydrogen bonding. So it is difficult to overcome these intermolecular forces, and that's why it has got a higher boiling point. Likewise, there is one more question given in your textbook. Why at room temperature ethanol is a liquid, whereas dimethyl ether is a gas? The first question which comes to our mind, why they are comparing ethanol with dimethyl ether? That is because both of them, they have got the same molecular mass. And if they have the same molecular mass, they have the same van der Waals forces. They have same van der Waals forces, they should have the same boiling point. But ethanol, along with these van der Waals forces, has got hydrogen bonding. So it is difficult to overcome its intermolecular forces. And that's why ethanol has got a higher boiling point. So ethanol will have a higher boiling point due to the presence of prominent intermolecular hydrogen bonding. Next, we'll talk about some phenols. One more question based on this. See, as far this point, boiling point is concerned, I've already told you two questions from your exercise, and now I'm telling you the third one. Based on based on the boiling point of phenol, one more question is given there. Here I have two compound, that is, they are the derivatives of phenol. I have this compound. This is orthonitrophenol. I have another compound, and that compound is like this. It is para-nitrophenol. So first one is ortho-nitrophenol. The second one is para-nitrophenol. Both these compounds, they have got same molecular mass. So they have same van der Waals forces. So they should have the same boiling point. But the boiling point of orthonitrophenol is lesser than that of para-nitrophenol. And since its boiling point is less, that's why, therefore, orthonitrophenol is steam volatile. Here I would like to tell you what does steam volatility means. There are some compounds, see orthonitrophenol and para-nitrophenol, they both exist in the liquid state. So if I have got a mixture of them and I want to separate them, what can I do? Well, a prominent method of separating two liquid components is distillation. So I will try to use distillation in this case, in a mixture of ortho and para-nitrophenol. Any component which has got a lesser boiling point will distill out, leaving behind the other compound. But here is a problem. The difference in boiling point of these two components is very less. So the temperature at which one will evaporate is the temperature nearly that temperature, another one will also evaporate or will boil. So it becomes difficult to separate them. Moreover, their boiling point is so high that by the time we reach that boiling point, these molecules, they will undergo decomposition. So what we do, we generally pass steam in the mixture of these compounds. The component which has got a lesser boiling point will evaporate with steam, and it is said to be steam volatile. So in this case, when I am saying that orthonitrophenol has got a lesser boiling point, that means orthonitrophenol is steam volatile. So out of these two components, orthonitrophenol is steam volatile. If I pass steam in the mixture of these two compounds, orthonitrophenol will evaporate or will move out with the steam. The other question comes to our mind, why orthonitrophenol is steam volatile? Why it has got a lesser boiling point? So we'll see that. Well, if I talk about orthonitrophenol, the molecule of orthonitrophenol is like this. You have a OH group here, you have NO2 group here. By withdrawing pi electrons, oxygen will have a negative charge and hydrogen itself has got a positive charge. So they will have intramolecular hydrogen bonding. So in orthonitrophenol, there is intramolecular hydrogen bonding. Maximum two molecules of orthonitrophenol can exist together. It can exist in dimeric state. So you will observe them like this. This is orthonitrophenol. Now what about para-nitrophenol? If I talk about para-nitrophenol, it forms long chains, endless chains. So here I can see a chain of orthonitrophenol like this. This is one of the chain I am having. This is one of the chain I am having of para-nitrophenol. Likewise, I'll have another chain above and below this. The OH from one chain will form hydrogen bonding with another chain, NO2 group of another chain. Likewise, the NO2 group will form hydrogen bonding with OH group of another chain. That means in orthonitrophenol, we have intramolecular hydrogen bonding, whereas in para-nitrophenol, we have long chains which are held together with large number of intermolecular hydrogen bonds. And it becomes difficult to break these intermolecular hydrogen bonds. It is very difficult to break these large number of intermolecular hydrogen bonds. That's why para-nitrophenol will have a higher boiling point as compared to orthonitrophenol. If para-nitrophenol has a higher boiling point as compared to orthonitrophenol, that means para-nitrophenol is not steam volatile, it is orthonitrophenol which is steam volatile. So this is an exercise question given in your textbook. So you can see this. So based on boiling point, we have done 3 different questions from your textbook. Like why alcohols have a higher boiling point as compared to corresponding hydrocarbons, why ethanol is a liquid and dimethyl ether is a gas at room temperature. Among ortho and para-nitrophenol, why orthonitrophenol is steam volatile. So we have seen because its boiling point is lesser, that's why it is steam volatile and its boiling boiling point is lesser as compared to para-nitrophenol because it does not have intermolecular hydrogen bonds. Para-nitrophenol, which has got large number of intermolecular hydrogen bonds, will have a higher boiling point because it is difficult to break these intermolecular hydrogen bonds. After that, this is all about their physical properties. After that, I would like to tell you something about their chemical properties. No doubt we are not going to start them now. We'll start them in the next class. We'll see their chemical properties. Chemical properties. If I talk about their chemical properties, their basic structure is like this. R CH2OH. So their properties can be divided into three main types. That is reactions involving breaking of oxygen hydrogen bond, reactions involving breaking of carbon oxygen bond, and reactions involving whole of the alcohol molecule. So we can divide their chemical properties into these three parts. As far as the first part is concerned, in that we'll be dealing with the acidic character of alcohols and phenol. Why alcohols are basic, why phenols are acidic, we'll be doing that. So this is all which we will do in today's class, and we'll be doing the acidic and basic character in the next class. Thank you very much. Thank you.